Welcome to all. Myself Dr. Santosh Singh, working as an Associate Professor in Department of Physics, Institute of Aeronautical Engineering, IARE. So we are discussing a topic semiconducting optoelectronic or semiconductors optoelectronics, and today we will discuss about EK diagram. EK diagram. So first of all, I want to recall some facts about band structure. So what you have seen in my previous lecture? You have seen a single non-interacting atom like hydrogen, or we can say one proton and one electron atom, one proton and one electron atom, like so same as a hydrogen atom case. So for such type of non-interacting system where one proton and one electron is only, so what you will get after solving the Schrodinger equation for such type of system, you will get sharp energy levels, okay, for single non-interacting atom. Okay, but this is not actual case. All the materials or any components or any solids have a several atom, and that atoms also have a many number of protons and many numbers of electrons surrounding it. Okay, so when we deal with the actual situation, then what we will get? We will get a band-like condition. Band-like condition. Not a sharp energy level. That sharp energy levels for an interacting atom will convert as a bands, energy bands. Okay. First case, only one atom. When number of atom is more, that energy levels will converted and form a bands. Okay. So what is the important term? Why? We already solved this thing. What is this? This is a Schrodinger equation. Time independent Schrodinger equation, and solving this equation for any considered system. Either it will be single atom or many atoms which are arranged in periodic manner. Okay. So solving this equation will give you the energy value. Periodic energy value or energy value. Allowed energy states. Okay. So when I solve qualitatively for single electron and proton atom or single isolated atom, this Schrodinger equation, what I get? I get a sharp energy level. So here this potential energy term is there. Okay. And but when we consider this many electron atom system, okay, so this potential energy term is become very complex, very complex. And also when I solve for single atom, we will get the single allowed energy states. Okay, single allowed energy states. But when we consider two atom, why? Because I discussed the case of two interacting atom. So I get two for each allowed states. I get two energy levels. Okay. Why I am discussing this? I want to give an emphasis what I told in previous lecture. Means 7 crystal system. Any solid can found in a form of 7 crystal structures or 7 crystal system, and it can be further classified in the form of 14 Bravais lattices. So at that lecture, I give all the details about what type of 7 crystal system exist and how they further classified in form of 14 Bravais lattices. So at that time I told that it will be helpful. So now I am able to give the answer of this question, how this thing, that arrangement is helpful. So answer of this question is, you can see the effect of, you can see the number of atoms and also their arrangement in band structures. Why I am telling? If you will get if you will calculate the Schrodinger equation for 2 interacting atoms, then each allowed energy state will come like 2 closely spaced levels. So there are an interacting atom. Why? Every solid is made with number of atom, and that number of atom is arranged in some fixed way. What is the fixed way? 7 crystal system, and further it will be classified as a 14 Bravais lattices. Okay. Now what is the arrangement? Suppose if you consider the case of simple cubic system, so if you know that this atom is arranged in simple cubic system, then you can try to estimate what the potential value around any atoms. Okay, what type of potential should be. Okay, now if it will be go for BCC, FCC, or monoclinic, triclinic, rhombohedral, hexagonal. So according to that, you can imagine the potential around any atom. Why potential? Why one term is came here. What is this? This is Schrodinger equation. E minus V upon multiplied by psi is equal to G. So this V is what? Potential energy. So how the potential energy developed around any atom? It will be developed based on a arrangement of atom. So how the atom is arranged in any solid? This way. 7 crystal system and 14 Bravais lattice. So you must know about some basic of this thing. Means 7 crystal system and 14 Bravais lattice. Why? Because this thing only govern the different type of atomic arrangement. Okay. So that thing is written here. So 7 crystal system, you know, that 7 crystal system will further classified in the form of 14 Bravais lattice. That will tell the whole arrangement, how any solid will arrange inside his environment. How any solid, the atom is arranged inside. So if you know this 7 crystal system and then further 14 Bravais lattice, then you are able to give the answer. Now, in actual situations, atoms are arranged in a 3 dimension within the different Bravais lattices for different crystal structure. So hence different type of potential. See what I already discussed. Different type of potential are interaction in different direction. So potential will be vary in every direction. If in case of simple cubic, it's okay. The potential will be same in all direction. But suppose in the case of rhombohedral lattice, so definitely in x direction the potential should be different. In y direction the potential should be different. In z direction potential should be different. So basically this band structure is not a 2D plot, it is a 3-dimensional plot. We are unable to plot here due to our limitation, but this is a 3-dimensional plot. Okay, first thing. And the second thing is, it is not a similar band. For qualitative picture, you can imagine as a band, but in 3 dimension. Why? Because due to your atomic arrangement inside the crystal, the potential is different. So in every direction, the energy level should be vary like that. So suppose I am plotting this thing for x direction. This is y direction. This is, suppose this is z direction. So overall, if you want to analyze anything, any energy levels, so at any particular point, what is the cross section value for each levels? So at that point, that is the energy value. Okay, means what I am telling. Suppose this is your one band. Generally, you imagine a sharp energy level are bands. Okay, so but not, this is not the case. Your actual band is like that. Okay, your energy level is like that in actual solid case. In actual solid case, in practical solid case, it will be like that. Means curve type of structure, not a straight line. Okay, so that thing is written here. This arrangement will leads to complex type of energy bands. Okay, complex type of energy bands, not a flat energy bands. Complex type of energy bands. These energy bands are known as a band structure of system, band structure of that solid, or EK diagram. Basically, it is a energy versus K diagram. Before today, I only take this energy on this y-axis, but I never chosen any parameter on this x-axis. Now I will choose K, vector K on this x-axis. So basically, this is the E versus K curve, EK diagram. This diagram is known as a band structure, and that band structure is useful for governing or give some subtle information about optoelectronic property. Okay, this you can't estimate anything from these bands, these flat bands. It is only helpful for determining either it will be semiconducting nature or insulating nature or metallic nature, but not more than that. But if you have some EK curve, so you can estimate the exact band gap value at different K points. And what is the nature of your band gap? Either it will be direct or indirect. Okay, and you can also predict it is useful for optoelectronic application or not. Okay, so that thing I want to cover in this video lecture. Okay, so from the energy bands in solid, we generally characterize the metal, semiconductor or insulator. But these energy bands diagram do not give more information about optoelectronic application. And to more about the optical and electrical properties of material, you have to go to the EK diagram, which is called the band structure. Okay, band structure, EK diagram. Okay, this is known as a band structure. EK diagram. Okay. So now, if how it will arise. So the first thing is atom is arranged in a periodic way. I already told periodic. Suppose this is the interatomic distance A. Okay. So everywhere the interatomic distance should be same. Why? That's why the periodicity will be maintained. So now I am considering, if I take the 1D arrangement for simplicity, the periodical arrangement leads to the periodic potential variation. So this atom also have some charge. Nearby any atom, the potential variation is like that. Okay. If you consider one atom, and this is the distance r, so the potential variation, when you reach closer to the atom, the potential will become infinity. So the potential variation both sides of the atom is like that. Okay. So if I consider n number of atom, so this potential is also varies like that. Means you can say that these potentials are also in periodic in nature. See here, same type of potential you have found throughout the lattice or throughout the crystal structure. Why? Because the atom is arranged in a periodic manner. So the potential which is generated by that atom is also in periodic in nature. So this thing is written. If I take the 1D arrangement for simplicity, the periodical arrangement leads to the periodical potential variation. The motion of electrons. Now, if any electron will try to move inside the crystal, so the motion of electron in crystal is governed by the law of quantum mechanics. Okay, and that electron will influence by such type of potential when that electron will try to move inside the crystal. Okay, so the same thing is written here, and also that electron motion will govern by the quantum mechanics. You have to solve the Schrodinger equation for that electron in such type of potential. So the same thing is written here. The motion of electron in a crystal is governed by the law of quantum mechanics. And if you have one electron, one proton system like the hydrogen atom, it is very easy to solve the Schrodinger equation. But this is not a realistic situation. This is not a practical situation. But in solid, where there are large number of electrons and atoms present, it is extremely complicated and difficult to solve the Schrodinger equation. So this thing, if you consider a single particle in a box, okay, so this is your potential value. You can solve this. Why? Because this particle is not interacting with any other kind of other particle, so you can easily solve. But if any electron will try to move from here, so they will influence by potential. Which potential? They will influence by potential generated by this atom also, this atom also, this atom also. So what is the exact potential there at a particular time t? You can't say. Okay, so it is very complicated. So but we need to solve anyhow. So we take one assumption, and that assumption is taken by one scientist named Bloch. F. Bloch observed that since the potential varies periodically, the probability of finding an electron should also vary periodically. They taken one assumption. What he suggested, since if this is the periodic potential, well, and if any electron will try to move inside this periodic potential, so whatever the wave function associated with that electron will also have some periodic nature. Means if suppose at any particular point its wave function is psi, then after some periodicity it will be same. So here periodicity is what? A. Why? Because after a distance same type of environment will be present. Okay. So that is the main consideration. So psi is wave function. Actually psi is what? Wave function, and mod of psi square will give always the probability of finding the particle. Okay. So if you take the mod and square it, it will give the probability. That's why psi is probability distribution function also. So the same thing is written here. The probability of finding an electron is equal to mod of psi square, where psi is the wave function. If the probability varies periodically, the wave function should also vary The wave function should also vary periodically. Means what he tried to say, whatever the wave function, it should be periodic in nature. Why? The variation in potential also in periodic. That's why wave function should also be periodic. Okay. So therefore Bloch postulated that in such a periodic medium the wave function should be in the form of this. What is this? This is a wave function. Your initial wave function at any particular k point is equal to UKR e to the power I k dot r. So generally this is the wave. Wave function is a wave. This is the periodic function. That is, the wave function is a product of plane wave e to the power I k dot r. This is the normal wave function, and this periodic term is introduced here, multiplied by the periodic function UKR. UKR. This is the periodic. This function has some periodic nature. Okay. So that whole wave function will become periodic in nature. So what is the periodicity? How? UKR is defined like that. Means UKR plus A is equal to UKR. Whatever the value of this function at R, the same value will come after time A. So this is the period. Here period is what? A. So okay. So if you substitute this form of wave function psi, okay. So what? This is your considered wave function. This is your considered wave function. Okay. Now, so you can put this wave function psi here. What is this? This is Schrodinger equation. Time independent Schrodinger equation. I also request to please remember this thing and also understand, try to understand. Remember what? This Schrodinger equation. Okay. So if you consider any kind of wave function, then that wave function must satisfy the Schrodinger equation. So what is the Schrodinger equation? This one. So if you put that type of wave function in Schrodinger equation, what you will get? You will get eigenvalue. You can solve for energy. Here E is the energy eigenvalue and V is the periodic potential. V is also already considered inside the lattice. V is periodic. and m is the mass of the electron. So energy eigenvalue also turn out to be periodic in K. When after solving the Schrodinger equation, whatever the energy value, you will get this energy value also have some periodic in nature. Here periodicity is defined by A, but that when you solve this Schrodinger equation, after solving you will get the energy value, and that energy value have periodicity in form of K. Okay, K, wave vector K, which means, if you plot energy E versus K, then corresponding to every energy level of single potential well, you will get the periodically varying energy value. Okay, so the value of K is shown in EK plot. Okay, whatever the plot. Okay, so what is the plot? What is the case? Del square psi plus 2m upon h cross square E minus V is equal to psi is equal to 0. E minus V multiplied by psi is equal to 0. This is your what? Schrodinger equation. Now what you considered? One wave function psi have a form of UKR e to the power I k dot r. Okay, so see here, UKR e to the power, you can also write like that, psi kr. Okay, now if you put this psi value here and solve this equation for energy, you will get energy eigenvalue which have periodic in nature, and which variable will show the periodicity? K variable. Okay, first thing. So solving the Schrodinger equation, what you will get? You will get the allowed energy state. Okay, allowed energy state. So for any type of system, after solving the Schrodinger equation, you will get the allowed energy state. Here you will get the allowed energy state, but that energy state will be periodic in K. So what you will get? You will get available or allowed energy bands in the form of okay. What I am trying to say, whatever the solution you are getting after solving the Schrodinger equation, del square psi 2m upon h square E minus V upon psi is equal to 0 after solving the Schrodinger equation with which type of wave function? The wave function which have a periodicity psi kr. Psi kr is equal to u k r e to the power I k dot r. If such type of wave function is used in this Schrodinger equation, then after solving this Schrodinger equation, you will get the energy eigenvalue, allowed energy eigenvalue, and this energy eigenvalue also periodic in nature. Periodic in nature means if you plot periodic in nature with within the K. So if you plot the allowed energy eigenvalue for one dimensional arrangement of atom, what you will get? You will get a wave-like bands which have some periodicity. Okay. Which have some periodicity. So actually this is a wave. In one direction this is amplitude, in opposite direction this is amplitude. So whatever the maximum total displacement in considering both direction, these things are considered as a allowed energy states. These things also considered as a bands. Okay, these are allowed energy states. Here also the same thing, whatever the considered displacement of this so-called wave, this is also known as a band. Okay, and this thing is known as a energy gap. So this allowed energy bands is in periodic in nature, so that if you know the property of this band in any particular region, so the same thing will be repeated in each and every period. Okay, suppose here minus pi by a to plus pi by a. Okay, again this is the region minus 2 pi by a. This is the this region plus pi by a. So you can see the same thing is repeated after pi by a. Here the same thing is repeated minus pi by a. This minus pi by a to plus pi by a region is known as a first Brillouin zone. Okay, so this is the very important thing. Whatever the property of crystal extended throughout the crystal structure, you can calculate the same property in this first Brillouin zone. In my very first video lecture, I already told we only considered the first Brillouin zone property. Why? Because the same property will be repeated. Why the same property will be repeated? Why? Because this allowed energy states wave function have a periodicity in nature. Okay, so this is your first Brillouin zone. Okay, so now if we omit all these things, so if we omit all the extended thing, this is your reduced zone scheme plot. And if we take this graph here, why? Because the same thing is repeated. Here again, if so this is your extended zone plot. So which one is important? Reduced zone scheme. Reduced zone scheme. Why? Because in first Brillouin zone, whatever the property throughout the crystal, you will get the same property. Okay, this minus pi by a to plus pi by a. Okay, this is your k axis, this is your e axis. Okay, so that's why in many contexts you see only this diagram. So this is your top of valence band. Why top of valence band? Because I solved the Schrodinger equation for a moving particle inside the crystal. So which particle easily can move? Which try to move from valence band to conduction band. That's why the conduction will happen. So this is the first energy level is your valence band region or valence region. This is your complete valence band up to here to here. And this is your conduction band. Conduction band. This point is known as top of valence band. This point is known as bottom of conduction band. Okay. So these 2 points are very, very important. If you know these 2 points, then only you can determine the energy band gap value. Energy band gap value means difference between this point to this point is characterized as a Eg. Okay. So I think this is okay for today video lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.